Hi, can you hear me?
Yes.
So I'm Spiniello. It's such a pleasure to be here, and not only for the beach, the sun, the free tequila, and so on and so forth, but also because I have the chance to present a work that has been done in collaboration with Mark Sarsi and Pavel Kranovic on gradients, spatial gradients of the low mass and of the initial mass function in M87, and I will also present you evidence for a gradient, spatial gradient in the sodium abundance in this galaxy. So to begin with, we had quite a lot of discussion already about the non-universality of the low mass and of the initial mass function for LB-type galaxies, and in particular since the Corrine-Van Dokken paper and the Capellari Nature paper in 2012, it's clear, at least to me, that the IMF cannot be universal for massive LB-type galaxies. But since then, we got several ideas or suggestions for what could be the driver behind IMF variation. The first one, and the most famous one probably, I'm sorry, here, it's the IMF velocity dispersion variation. This is my personal plot of this relation. And as you can see though, a lot of the authors using different methods, so stellar population modeling, lensing plus dynamics modeling, and also only dynamics like Capellari et al., they all agree that, or agreed, I should say, that the initial mass function gets steeper when you go to more massive galaxies or to higher velocity dispersion, to galaxies with higher velocity dispersion. Then in 2015, Martin Navarro and the Khalifa team suggested that the variation is actually driven by total metallicity. It's tighter with total metallicity. And again, a richer galaxy with richer metallicity seems to have a more larger number of dwarf stars, so stars with masses, let's say, below 0.5 solar masses. And then Russell-Smith came in 2015, and he actually found three very massive galaxies with velocity dispersion above 300 kilometers per second, showing a normal universal Milky Way-like IMF. And this created quite a lot of problems, and one attempt to solve this problem was the anti-correlation we found between IMF slope and total density by using lensing dynamics and stellar population combined together in the X-lens survey, for which I'm the PI. So basically, if we believe that the initial mass function is not universal, then now we should focus on understanding what drives, what's the physical driver, why IMF is variating, and in correlation with what galaxy property, which galaxy property. So if we believe the two-phase formation scenario in which very massive early-type galaxies have formed through first very quick and violent star formation events, and then they accreted material later on in time, we would expect, if this has to do, if the IMF is variating because of the, let's say, properties of the universe during formation, during the collapsing of the cloud, as Hopkins proposed in 2007, then we might expect that the bulk of the population confined in the very innermost region of the galaxy could have a bottom-heavy IMF, whereas the accreted material, which is coming from smaller systems that have been formed later on, could have a normal Milky Way-like IMF. If this is true, then we should expect to find, observationally speaking, spatial variation in the IMF. And we thought that MUSE could be a great instrument to check for that, thanks to the integral free spectroscopy over a very big field of view that allows you to go further away from the galaxy center, having a continuous coverage, but also thanks to the spectral coverage, because we do need to go in the infrared to observe the initial mass function sensitive indicators, but we also need to break the generations with age, metallicity, and elemental abundances, and blue indicators are better in order to do that because they are completely IMF insensitive, non-sensitive. And that MUSE has a huge sensitivity, a great sensitivity that allows us to have beautiful, high senior to noise spectra in few-hour integration time. Actually, this is just 1 hour integration time. That's science verification data on M87. And here we only observe with 1 hour, and nevertheless we can reach amazingly high senior to noise by binning the spectra using by Spiniello and Galaxy using two different approaches. The first one we did annular, we bid the data in annular spectra, so basically same distance, same radial circular distance from the center, and by doing that we obtained similar to noise of both 2000. And the spectra shown here, we highlighted some of the IMF sensitive features in the red and the usual link indices to constrain energy and metallicity. By the way, we had to exclude the very innermost spectrum because it was highly contaminated by emission lines. And then, in order to save the spatial information a little bit more, we decided to use a Voronoi 2D evening technique by Eric and Michele and Seller Capellari. And in this way, we set a threshold of 300, and we had something like 400 spectra with this similar to noise, and this is high enough to constrain the IMF at the very low center. So what do? We use equivalent width. That means that we measure line strength indices. We have those IMF sensitive features, and that just to be sure that everybody knows what I'm talking about. Here I'm using a plot from Corroy and Mandokov in 2012, in which I'm using singles, it shows single stars. The red one is an M-dwarf, and here you can see the sodium line and the Winford line showing up only in the case of an M-dwarf stars. Here is exactly the same, just a different way of plotting it. This is the full Miles library, such as Blast, it's a tool 2006 if I'm not wrong. And here I'm plotting the equivalent width of one of the IMF sensitive indices I characterized in 2014 against effective temperature, and as you can see, it's only strong, actually it's only there in case of cold stars and gravity. And as you can see, it's strong only in case of dwarf star. So far, this is the only poorly low mass end indicator for the IMF. All the other indicators are gravity sensitive, meaning that they are strong, the equivalent width is strong both for giants and dwarf. They are still nevertheless useful to constrain the giant to dwarf ratio, but this is the only one that allows you to, at least in the optical, that allows you to count low mass star. So we use simple stellar population models, both from Muscat, but that is a plot, and Corroy and Mandokov in 2012, and we compare the equivalent width of each spectrum for M87 with the equivalent width of the same features of in simple stellar population models, where we got in the alpha varietal, the IMF, and the total emittability. The age was fixed to 11 gigayears because unfortunately H beta is contaminated by emission lines. And we're confident that this is okay because for all stellar population, for galaxies with all stellar population, age, it's not that, the age IMF degeneracy is not that strong, let's say above 9 years, and there are no age gradients reported for M87. We used 11 gigayears estimation by Montes et al. 2014. Then to a very simple chi-square minimization, we find the best fit parameter for each spectrum, both for the aperture approach and the Voronoi spectra, and those are some results. Let's start with the aperture results. Again, this is similar to noise 2000, so this is a really good data. We find an IMF gradient in the sense that in the innermost region of the galaxy, the IMF tend to be bottom heavy, so more dwarf stars, and it goes down up to roughly a salpeter value around the 30 cells. And it's the slope, the steepness of this variation depends on the model you adopt, but nevertheless, there's no way the IMF can be universal over the radius, so there's a gradient. There's a very strong metallicity gradient, and the offset is again, it depends on the adopted set of indices and on the model. But the slope of this gradient stays roughly the same. Whereas alpha to iron profile are flat, maybe a little bit of a gradient is shown by using the Muscat models, and extended means that we had to extend the parameter space of the models through response functions. But nevertheless, it stays super solar for the whole radius range. Same is valid for the Voronoi bending results. However, here more structure can be seen in the radial profile, and in particular in the IMF gradients, you can see that there's a sort of a plateau in the innermost 5 arc segments. And this is kind of confirming or going into the direction of the two formation scenario, in the sense that here you're tracing the innermost stellar population, which has been formed in the first star formation burst, if you want, and here you're tracing the accreted material somehow. It's just tentative and I'm not claiming anything, but you know, it's interesting to see that the Voronoi results are showing more structure in the radial profile. Even more interesting, in my opinion, we should try to search for correlation between the IMF gradients and characteristics of the galaxy, parameters of the galaxies. And as it was already anticipated, the IMF gradient by Maria, for instance, today, the IMF gradients do not seem to follow, do not seem to follow velocity dispersion very well, and they fit much better to, with the total methodicity gradient. Here you can see the Martin and Navarro results that Maria presented. We are offsetted, but as I said, this offset can change by changing the stellar progression model or the set of parameters you're using. And this is my very last slide, because my time is running over. Sodium over iron is variating very, very strong in this galaxy. It has a super solar value everywhere, so it never goes below 0.4, I would say, and it goes up to 0.6 in the very innermost region, but it presents a gradient, which is as strong, if not stronger, than the IMF gradient. So take-home message, we really have to pay attention to the sodium features if we're using only those features to constrain the IMF, because sodium features are much more sensitive to abundance than to IMF. Results is in agreement with other literature results involving elemental abundance changes and gradients in L-type galaxies, in massive L-type galaxies. Those are my conclusions, but rather than read my conclusion, I will leave you with my future work slide. And this was just a pilot program. We got really, really excited by MUSE and by its great sensitivity, but we have several instruments within MUSE. We're observing new data now, and the data reduction is improving. Then there's CALIFA, which is still wide enough in terms of wavelength range to use the IMF indices. And then MANGA, that allows us to have a statistical, meaningful number of galaxies and see whether we can reproduce correlation in the full population of massive galaxies. Plus, we should really move to the infrared, as was already said today, because there the contribution of M dwarfs is much stronger in the light spectrum. Thank you.
We have just one question, but I want to make just a note. You mentioned that, of course, I like a lot the results, but when you mentioned the Martin Navarro result, you said that the correlation is with the total metallicity. Actually, there is partial result, so there is a correlation between the IMF and the local metallicity. Yeah. And since there is a gradient with local metallicity, the results are even more in agreement, because we also show this chain from the inner part to the outer part. It was not highlighted in that way in the article, but when you see a spatial result point, just...
I agree, and I'm sorry I didn't.
Yeah, we agree.
But yeah,
sorry.
I completely agree.
So one question... Oh, sorry.
Now I have to decide.
Sorry.
That's okay.
Well,
Very quick, which masses are you sensitive to this method on IMF?
I would say everything below 1 solar masses. Everything above 1 solar masses is already dead in my galaxies. And concerning the method, different indicators are sensitive to different mass beams. So in theory, if your beta are good enough and you believe in your model enough, you could disentangle, you could count into mass beams. But I don't think we're there yet.
But what's the range then?
The range, I would say, between the theoretical range, it goes between 0.08, which is the hydrogen burning limit, and I would say 1.2 solar masses.
Oh.
Yeah, that's the range.
Okay, so I have a question. I mean, when we talk about radial gradients for in a spiral, I come from the stand that the orbits of stars more or less permanently alive at that radius. But for an elliptical, of course, in M87, it's entirely pressure supported. The stars move on through all radii. So, the gradient you see within M87 of the IMF must mean that as a function of orbital energy for the stars, the gradient is even more steep, right? It has to be really, really, really steep as a function of orbital energy to create this observer line, because the stars move radially. So, I mean, which mechanism do we know that creates such a steep gradient?
That's a great question, but I don't have an answer to that question yet. But I agree. And it has also a great implication for the mass vibration that goes into black hole masses. It's a physical matter. Physically, it's a very important problem, but so far we only have questions. We don't have answer yet. Sorry.
Okay, last question.
Tara, I hope you can help me out with this question I got from a student recently, and they asked me whether we have a quantitative assessment that we know the lifetimes of giants precisely enough that what we're measuring is not more or less dwarf stars, but differing time lifetime with mechanicity. Do we know that? Do we have a quantitative assessment?
We kind of know that. Okay, so we know that indirectly. First of all, I believe that KH1 indicator is quite important because that one comes only from dwarfs. So if we measure equivalent width of that particular index, and this is very strong, we know that we're not measuring giants.
Not only that, because the equivalent width is, the continuum level of the equivalent width is set by the giants, right?
I completely
It's
agree.
always measuring giant to dwarf ratio.
You're right. Then the answer is no, we don't. And that's why I think we should always talk about fraction of giant versus dwarf and mass ratios, because those are the feasible ones.
Okay, let's, thanks again.